So very good evening and welcome you all in the fifth PhD thesis reading session. And the topic of PhD thesis is the design of directional coupler based silicon optical modulator, submitted by Mr. Himanshu Das for the award of PhD degree in electronics and communication engineering. So in last 4 days we have completed 4 chapters. Just as a review, in chapter 1 the literature survey, motivation, objectives, problem formulation, scope of research, major contribution of thesis, significance of research outcomes, and organization of thesis have been discussed. And in second chapter, we come to know about different kinds of electro-optic effects, losses in optical waveguides, performance matrices of optical modulator, and different kinds of optical modulators also. Then later on, we did mathematical modeling of directional coupler based optical modulators, followed by application of optical modulators. After that, the third chapter was a contributory chapter in which the modified side wall angle based waveguide electro absorption modulators were was basically feature of this chapter. Then yesterday we come to know how to compare VO2 and ITO based electro absorption modulators. And then today we will cover a V-shaped ITO based electro absorption modulator and then conclusion and future works. So chapter 5 is also a contributory chapter, and latest article was published in Journal of Modern Optics. So with this small, without taking much time, I would like to invite Himanshu Das to go ahead, and I request further participants, please take part. Feel free to ask any question. No question is as such silly. We want to hear you either in form of feedback. Criticism is also very much welcome. Suggestions are also very much welcome. As well as there should be some curiosity from your side, so that we should also know whether we are able to communicate with you or not. So with this, I again welcome you all. Madsi, Balvinder, Indrani, Himanshu, then Shubhranshu, Bhargavi, Barkinti, Muthu, Amartya, Deep, and yeah, few left, Likinti, yeah, everyone. Okay, so with this, over to you, Himanshu.
Thank you very much, sir. So today we'll be reading the chapter 5 of our thesis, and the title of chapter 5 is a V-shaped ITO-based electro-absorption modulator.
Let me synchronize. Okay, let me come on the chapter 5. And if it is visible, please let me know also, so that all audience should be able to see it properly. So chapter 5 is on starts from 67 number page. I think it is still loading. What happened? Why this is? Actually, in Shillong, it's heavily raining. Maybe because of that, network connection is a little bit slow. Please bear with us. I have again refreshed.
Um,
Screen is visible.
yes, sir.
Okay. Now this is chapter 1. Then, yeah, chapter 2. Then chapter 5. Yeah. So the title of chapter number 5 is a V-shaped ITO based electro absorption modulator. Yes, Himanshu, you can continue.
Okay, so let us start from section 5.1 introduction. The unprecedented COVID-19 situation across the globe has compelled people to live with new norms of life. Most people work from home. This needs a seamless, uninterrupted, efficient, robust, cost-effective, massive scale of photonic integrated circuits (PICs) and optical fiber wireless communication infrastructures. Reference number 81, 82. Moreover, high-definition television (HDTV) distribution, online network games, interactive multimedia services, HD, virtual reality, VR, online classes for academic purposes, webinars through online platforms like Zoom and Google Classroom have been presently in use to an extent like never before. Reference 8325. The massive demand of miniature PICs and high-speed optical communication can be increased by utilizing plasmonic material-based devices such as ITO and VO2-based electro-absorption modulators (EAMs). Reference number 6, 55, 78, 86, 87. In recent past, researchers across the globe have reported ITO plasmonic material-based EAMs. Reference 8, 9, 15, 51, 53, 79. With appreciating results to silicon plasma dispersion effect based optical modulators. Various configurations of optical waveguide structure and optimization of device dimensions have been investigated and discussed in this chapter to improve the performance matrices of ITO-based EMs. Further scope of improvement is possible by carefully selecting the dimensions and geometrical structure of the device. A thorough optical characterization of the promising feature of ITO, like the unique epsilon near zero ENZ characteristic, have facilitated the plasmonic material to be used in optical modulators as an active material that works on the principle of capacitively induced accumulation layer formed at the ITO/dielectric interface upon applied potential. Reference 5288. In this paper, a V-shaped ITO plasmonic-based EM with different waveguide heights and design are designed, and its performances are investigated and compared in terms of ER, IL, and FOM, respectively, along with the contemporary ITO-based optical modulators. The device's structural parameters are also optimized in terms of waveguide width, height, and thickness of the plasmonic material used. The investigated V-shaped ITO plasmonic-based EMs consist of a Si-ITO HFO2 Si stacked upon a silica substrate. The light propagating inside the waveguide achieves stronger field confinement in the presence of a plasmonic material and a dielectric material when an electric field is introduced, making it a hybrid plasmonic waveguide. Reference 15. The effective refractive index of the medium changes upon applied potential as most of the light is confined tightly at the active layer interface, resulting in higher FOM. The higher value of FOM is related to the lower value of IL and ER's higher value. Now coming to section 5.2, design the V-shaped.
Can you give a pause here?
Yes, sir.
Here I would like to draw the attention of all audiences. See this paper, as you see, we started, uh, with this introduction, the unprecedented COVID-19 situation across the globe. While writing any article, etc., we have to be up to the what is called uh, up to date and contemporary problems or issues. If we are able to uh, take up into our article, that is really benefiting. It means from this writing itself, although work has been started long back, but since this chapter is, contributory, which is the last chapter, here from the text itself tells that how important this task is. So from our way of writing, we try to get into the publication domain. So this is how one can improve their writing skill or make their paper stronger. So one has to be very very contemporary. Okay. So and lot of references have been incorporated into this. So you can see Himanshu has just taken from that. That is why, in this paper the word is there. However, since now it becomes a part of thesis, and that to chapter 5, so we have to modify accordingly. Okay. So with this, yeah, let us move to 5.2. Before that, if anyone has any question, can ask. Anyone? Participants? No question, then we can move. Or somebody is asking. Please write in chat box also. Use the chat box. I think no question. So Himanshu, go to section number 5.2.
Okay, sir. Section 5.2, design of the V-shaped electro absorption modulator. A cross-sectional view of the V-shaped ITO plasmonic base EM is shown in figure 5.1. The 3D view of the device with the optical input and optical output modulated signal is shown in the inset of figure 5.1. The device consists of a SI-ITO HFO2 SI stick upon a silica substrate, where ITO is a plasmonic material with unique ENZ characteristic. So in figure 5.1, it shows the cross-sectional view of the device, that is the V-shaped ITO plasmonic material based electro-absorption modulator. So here we can see inside the silicon waveguide, there is a V-shaped ITO. There is a green color indicates the ITO layer, the black color indicates the HFO2, that is the hafnium dioxide layer, and the red color indicates the accumulation layer, which is placed in a V fashion inside the silicon waveguide. Therefore, we have given the title of our chapter, or we can say the paper, as V-shaped electro-absorption modulator. So from here, the name of the paper is coming. And the inset of figure 5.1 shows the 3D view. That is from where the input signal is coming and from where we are measuring or calculating the optical output. So it is showing the 3D view. And the electrical signal is applied to the ITO layer. And here the height of the waveguide, that is the SI waveguide, is 350 nanometer, and the width of the waveguide is 320 nanometer.
From the audience side, any question regarding this image? So this optimum length, width, and height, and its position, etc., are the design issues. Thickness, the way we have seen in earlier chapter also. Same here. Only issue that earlier it was only this rectangular shape like this. But if we take this kind of shape, then there is an improvement in the performance further. Okay. Yeah. You go ahead, Vanshu.
Okay, the property of ITO changes from a pure dielectric to a metallic state on the application of applied potential, which gives it a tunable capability. ITO has high optical transmittance and good electrical conductivity. Reference 6 1587. Also, HFO2 is used as a dielectric material to tolerate a high electric field at lower bias voltage inside the SI waveguide. Reference 11. The ITO HFO2 is sandwiched between the SI waveguide, which allows to control/manipulate the light propagating inside the waveguide. Moreover, the materials SiITO HFO2 Si is compatible with CMOS technology. The width, height, and length of the waveguide is 320 nanometer, 350 nanometer, and 500 nanometer respectively. The ITO HFO2 layer is placed inside the SI waveguide in a V-shaped fashion. The thickness of the ITO and HFO2 layer is 12 nanometer and 5 nanometer respectively. ITO is a plasmonic material and a refractive index can be calculated from its complex permittivity obtained from the Drude-Lorentz model from equation 3.1, 3.2 and 3.3 of chapter 3. The value of material parameters taken are same as the modified sidewall angle base EM in chapter 3. The complex permittivity of ITO is shown in figure 5.2a for different wavelengths. Wavelength 1530 nanometer, 1550 nanometer, and 1570 nanometer. The imaginary part Im epsilon ITO of ITO permittivity increases in the real part Re epsilon ITO decreases with an increase in the applied potential and reaches 0 at 4.45 volt at the communication wavelength of 1550 nanometer, which can be calculated from equation 3.1 chapter 3. At 4.45 volt, the phase of ITO changes from a pure dielectric to a metallic state. This is termed as ENZ condition. Also, the real n and the imaginary k part of ITO's refractive index can be calculated from its permittivity epsilon r equals to n minus ik whole square as shown in figure 5.2b. Figure 5.2c shows the effect of Vg on the carrier concentration of electron n at different thicknesses of the accumulation layer TACC. With an increase in potential, n increases as it is proportional to the applied potential calculated from equation 3.3 chapter 3. For TACC equals to 2 nanometer, n equals to 6.46 into 10 to the power 26 per meter cube at 4.45 volt. Further increasing the TACC, n decreases because TACC is inversely proportional to n. Moreover, breakdown potential of HFO2 layer is 5 volt, reference 11, and the maximum value of IL can be achieved at higher gate voltage bias, which is accomplished at a thicker accumulation layer. Therefore, a thickness of 2 nanometer is chosen as TACC, which is below 5 volt. The value of refractive indices used in the simulation where NSI equals to 3.47, NHFO2 equals to 1.98, NSIO2 equals to 1.44, and NITO as plotted in figure 5.3b. So coming to figure 5.2a, it shows the complex permittivity of ITO. That is, it shows the real and the imaginary part of the permittivity of ITO at different wavelengths, that is 1530 nanometer, 1550 nanometer, and 1570 nanometer. So here we can see the real part of ITO's permittivity decreases and the imaginary part increases with increase in potential. However, at around 4.45 volt for the wavelength 1550 nanometer, the real part of the permittivity of ITO reaches 0, which is termed as epsilon near 0 condition. So therefore, we are using this voltage, that is 4.45 volt, in our calculation as the off state for the device where the material can observe maximum amount of energy. And here there are two y-axis, that is one is for the real part of the permittivity and one is for the imaginary part of the permittivity, which is indicated by the arrow. And coming to figure 5.2b, It shows the real and the imaginary part of the ITO's refractive index as a function of applied potential at 1550 nanometer wavelength. So this graph, it is the graph of figure 5.2b, is coming from the equation of epsilon r equals to n minus ik whole square. Since we are calculating the permittivity in figure 5.2a, from here we can calculate the refractive index if we use the formula epsilon r equals to n minus ik whole square, where n is the real part of the refractive index of ITO and k is the imaginary part of the refractive index of ITO. Now coming to figure 5.2c, it shows the effect of applied potential on the carrier concentration at different thicknesses of the accumulation layer. So here we can see there are different thicknesses for the accumulation layer. That is thickness of the accumulation layer equals to 1 nanometer, 2 nanometer, 3 nanometer, and 4 nanometer. Here, with increase in potential, the thickness of the accumulation layer increases as this TSAC is proportional to applied potential V. However, here we have chosen 2 nanometer as the thickness of the accumulation layer. Now coming to section 5.3, results and discussion. Structural analysis of V-shaped modulator. When a potential is introduced to the ITO layer, the effective refractive index and effective of the device gets affected by the capacitively induced accumulation layer, thereby incurring a loss in the waveguide. These losses have to be optimized by changing the structural parameters to boost the device's performance in terms of ER, IL, and FOM respectively. Also, most of the light is confined around the active layer interface, which is when a potential is introduced. To tolerate the effect of a high electric field induced with low biasing voltage, a dielectric material HFO2 is used. When input power is introduced to the waveguide in the absence of applied potential, 0 volt, most of the light passes through the waveguide undisturbed, termed as the on state. Similarly, when potential is applied at 4.45 volt, most of the light gets tightly confined near the active layer region due to the ENZ condition, resulting in maximum absorption of light by the waveguide, which is termed as the off state. The light intensity at both the on state and off state for the V-shaped ITO plasmonic base EM is shown in figure 5.3a. Figure 5.3b shows the effect of increase in applied potential on the effective refractive index of the device, which results in a change in the IL incurred by the device. The NEFF increases rapidly from 1.91 to around 2.39 and decreases because of the ENZ condition. The IL decays exponentially when N moves away from Vg equals to 4.45 volt, corresponding to N equals to 6.45 into 10 to the power 26 per meter cube in both direction. Because when ER moves away from its minimum value, the optical power in the accumulation layer reduces and is redistributed to the HFO2 and Si layer. Also, NEFF is affected by the ENZ region as it is dependent on the epsilon r. The effect of an increase in the thickness of ITO on the IR of the device is shown in figure 5.3c. The maximum IL, around 11 dB per micrometer for the off state, was observed between 10 to 15 nanometer thickness of ITO. While maintaining a low IL of 0.25 dB per micrometer at on-state. The maximum energy traveling inside the waveguide is absorbed and tightly confined around the active layer at 10 to 15 nanometer thickness of ITO. Therefore, an optimum value of 12 nanometer is chosen as a thickness of ITO to achieve maximum ER in bracket IL offstate minus IL onstate. At low IL in on state without making the device footprint large. Similarly, to investigate the effect of waveguide width on the IL of the device, the waveguide width is varied from 250 to 500 nanometer and its corresponding IL is observed for both offstate and on-state as shown in figure 5.3d. The maximum IL observed was 11.06 dB per micrometer at offstate for 320 nanometer waveguide width. With further increase in the waveguide width, the IL decreases because the maximum amount of light is accumulated at the active layer region around 320 nanometer waveguide width. However, if 310 nanometer or 330 nanometer is taken as the waveguide width, an ER of around 10.4 dB per micrometer and 9 dB per micrometer respectively was observed. Therefore, to obtain a maximum ER of 11.04 dB per micrometer, 320 nanometer is taken as the waveguide width. Also, the transverse magnetic TE mode is not very prominent compared to TM mode, as the loss is very high in TE mode at on state, as shown in the inset of figure 5.3d. At a communication wavelength of 1550 nanometer, TE mode yields an IL of around 2.4 dB per micrometer, which is very high compared to 0.025 dB per micrometer for TM mode at on state. So here, figure 5.3a, it shows the light intensity of the device at both on state and off state. That is when no potential is applied 0 volt. At 0 volt, the light is allowed to pass through the device undisturbed. And when we apply potential of 4.45 volt, which is termed as the off state, maximum light is absorbed by the active layer, that is the ITO HFO2 interface. Therefore, at the output, maximum absorption take place inside the device because of the ENZ effect, which is also known as epsilon near zero effect. Now, coming to figure 5.3b, it shows the effect of an increase in applied potential on the IL and N effective of the device. So here we can see there are two y-axis. One is of insertion loss and other is of the effective refractive index. So with increase in potential, we can see for the insertion loss, which is indicated by the black line, with increase in potential, the loss increases. So maximum loss, or we can say maximum absorption, is found between the region of 4.45 volt. So maximum loss from this graph, we can see that maximum loss is around 4.45 volt. However, if the potential is further increased, then the loss decreases because as we have seen in the earlier figure that the permittivity for ITO, that is a real part of permittivity of ITO, reaches 0 at around 4.45 volt. However, if we increase the potential, then again the permittivity reaches some value. Although it may be negative, but it has some value. It is not 0. Therefore, in order to have an epsilon naught near 0 condition, the epsilon naught must be 0. So only at this ENZ condition, the phase of the material changes from a pure dielectric to a metallic state. So if the permittivity of the material goes away from 0 either in positive or negative direction, then it loses its property of dielectric to metallic. Therefore, it loses its property from a metallic state to dielectric state. Therefore, at around 4.45 volt, it is a fully metallic material. So that's why at this region of 4.45 volt, maximum absorption is there. However, further applying potential, then it tends to change its behavior from metallic state to dielectric state. So only in the region around 4.45 volt, the device acts as a metal. before 4.45 volt or after 4.45 volt, it is a dielectric material. That's why, because of this effect, there is a change in the effective refractive index of the device. As you can see, from the region of around 4 to 6 volt, there is a sudden shift. If we see the effective refractive index line, that is the red color line, there is an abrupt change in the curve from around 4 to 6 volt, because in this region the material property is changing from a dielectric to a metallic state. However, increasing the potential beyond 6 volt, again it tends to go to its dielectric state. Now coming to figure 5.3c, here it shows the effect of an increase in the thickness of ITO on the IR of the device. So what will happen if we increase the thickness of ITO on the insertion loss? So here we can see that for the off state, which is indicated by the black line, with an increase in thickness, the insertion loss increases. However, increasing the thickness beyond 15 nanometer, the insertion loss decreases. And we can see that in between 10 to 15 nanometer thickness, the insertion loss is almost same. Therefore, we have taken this 12 nanometer as the thickness of ITO material, because this is an optimum value in between 10 and 15. And here in the inset of figure 5.3c, we can see the on state and off state for the device at different thicknesses of the ITO at around 5 nanometer, 15 nanometer, 20 nanometer, 25 nanometer, and 30 nanometer. So coming to figure 5.3d, figure 5.3d shows the insertion loss as a function of an increase in waveguide width. So here, what will happen to the device, or what will happen to the insertion loss of the device if we increase the waveguide width? So here we have taken the reading from 250 nanometer to 500 nanometer. So we can see here at around 320 nanometer waveguide width, we have seen maximum loss at off state at around 320 nanometer waveguide width. So in order to have a good extinction ratio or a higher value of extinction ratio, we need higher difference between off state and on state. Since in on state it's negligible, the loss is negligible, so maximum value for the off state we are getting around 320 nanometer. So therefore, from this value, if you calculate, we will get a higher value of extinction ratio as compared to other waveguide dimensions. Therefore, we have chosen 320 nanometer as the waveguide width for the device. Also, the inset shows the IL in TE and TM mode over the wavelength ranging from 500 nanometer to 1580 nanometer. So in the inset, from the inset, we can see the effect of IL with the effect of increasing wavelength on the IL of the device for TE mode and TM mode. Here the red line indicates TM mode and the black line indicates TE mode. So from this diagram, it is obvious that we are getting maximum loss for TE mode in on state, but we want negligible loss for our device in on state. Therefore, we have chosen this TM mode for our device, because we want our signal to pass through the device undisturbed at on state. That's why we have taken this TM mode for our device, because if we choose TE mode, then maximum loss will occur itself in the on state. So now coming to figure 5.4a, it shows the effect of change in waveguide height on the IL of the device. So here, with increase in waveguide height, we can see the insertion loss increases. So at around 350 nanometer waveguide height, maximum IL is observed for the off state, which is indicated by the black line. So here we are getting around the insertion loss of 11 dB per micrometer. So beyond that, beyond this 350 nanometer value or decreasing the waveguide height, we'll get less value of IL at off state. Since we require higher value of ER, which corresponds to higher value of figure of merit, that is FOM, that's why we have chosen higher value of insertion loss at off state, which is from this graph figure 5.4a is only possible if we choose 350 nanometer as the waveguide height. Therefore, we have chosen this 350 nanometer as the waveguide height for our device. Also, figure 5.4b shows the IL as a function of change in waveguide width for the V-shaped EAM with 220 nanometer waveguide height. So in this chapter, there are basically two devices. We have shown two V-shaped devices, one having a 350 nanometer waveguide height and one having a 220 nanometer waveguide height. Because 220 nanometer is the current technology, we can say, which is applicable in today's technology. Therefore, we have taken this 220 nanometer height and 350 nanometer height, and we have compared both the devices in terms of insertion loss, extinction ratio, and figure of merit. So this figure 5.4b here, we have taken our device with 220 nanometer waveguide height, and we have observed or we have calculated at what value of waveguide width we will get maximum extinction ratio. So, or maximum insertion loss at off state. So from this figure, we can see that maximum value of insertion loss at off state is observed around 400 nanometer. Therefore, for the device with 220 nanometer waveguide height, we have chosen 400 nanometer as the waveguide width. And the inset shows the on state and off state for the device with 220 nanometer waveguide width, waveguide height having a width of 400 nanometer. So figure 5.4a shows the effect of change in the waveguide's height on the device's insertion loss. At 350 nanometer waveguide height, a maximum IL of around 11.06 dB per micrometer is observed at the offset, while maintaining a low IL of 0.025 dB per micrometer at the onset, which is suitable for achieving a high ER corresponding to a higher value of FOM. An increase in the height of the waveguide above 350 nanometer results in lower IL because the maximum amount of light is confined in the ITO-HFO2 interface around 350 nanometer waveguide height at offset. Further, increasing the height, the light gets diffracted throughout the stick, resulting in lower IL. Also, for 220 nanometer SY technology, the same V-shaped ITO plasmonic base EM is investigated by taking 220 nanometer as the waveguide's height. The effect of waveguide width on the IL of the device is shown in figure 5.4b. The maximum IL of 7.051 dB per micrometer is achieved at 400 nanometer waveguide width while maintaining a low IL of 0.031 dB per micrometer at on state. Therefore, 400 nanometer is taken as the waveguide width. Also, it supports single mode light propagation at 400 nanometer waveguide width. The inset shows the on-state and off-state of the V-shaped ITO plasmonic base EM with 220 nanometer waveguide height at 1550 nanometer operating wavelength. To date, various ITO-based optical modulators were designed to achieve better performance in terms of IL, ER, and FOM. The structural design of different contemporary ITO-based optical modulators are shown in figure 5.5. Figure 5.5a exhibits an ITO HFO2 layer with 10 nanometer thicknesses of ITO above the SI waveguide, thereby achieving an ER of 0.11 dB per micrometer and FOM of 36.67. Reference 8. Similarly, the structural design of figure 5.5b and 5.5c yields an ER of 4.83 dB per micrometer and 4.3 dB per micrometer with corresponding FOM of 161 and 1.65 at the expense of 0.03 dB per micrometer and 2.6 dB per micrometer IL, respectively. Reference 9, 10. Figure 5.5D shows the ITO HFO2 layer
Himanshu,
is inclined. Yes, sir.
this FOM of second one needs little bit abnormal. Please check it. Okay, this one. Is it really 1.65? Because this is
For
FOM
reference
or
number
one.
10. Okay, sir. I will.
Because it is one is 161 and another one is only 1.65. It may be 165. So please check it.
Okay, we can check it from the table itself because from there we can calculate. Okay, okay, I will check it. Okay.
Okay. Okay, go ahead.
Okay, figure 5.5D shows the ITO HFO2 layer is inclined at an angle of 84.09 degree inside the SI waveguide, resulting in an ER of 6.81 dB per micrometer and FOM of 337, reference 11. Also, figure 5.5E yield an ER of 1 dB per micrometer along with a FOM of 25 at the expense of 0.04 dB per micrometer insertion loss. Reference 59. Figure 5.5F and 5.5Z exhibits an ER of 2.71 dB per micrometer and 3.95 dB per micrometer respectively. Also, it has a FOM of 6.02 and 4.48 at the expense of 0.045 dB per micrometer and 0.88 dB per micrometer insertion loss respectively. Reference 6064. The structural parameters of different ITO-based optical modulators are shown in figure 5.5 are listed in table 5.1. Section 5.3.2 Performance analysis of the V-shaped modulators. The operating wavelength of
Before going to this, if anyone has question or need 2 3 minute or 5 minute break because it is about 1 hour going to. So let us have 5 minute break.
okay, sir.
What do you say, other members? We can have break little bit.
Yes, sir.
Okay, thank you. But be here, okay? Don't go away. Okay, thank you. Have a little bit break, 5 minutes.
Okay, sir.
So welcome back, Himanshu. Are you there?
Yes, sir.
Very good. So thank you all for having questions and still joining here. So can we move further?
Okay, sir.
Before moving, if someone asks a question, session is open. If no question, let us move. Five point 3.2.
Okay. Performance analysis of the V-shaped modulators. The operating wavelength of 1550 nanometer is taken for the V-shaped ITO plasmonic base EM to carry out the results.
Just tell something about this figure. Okay.
Okay, so here we can see that in figure 5.5, it shows the different structure or the different devices with which we have used to compare the result of our work from the literature. So these are the devices from the literature. We have used these devices and we have taken their results in terms of insertion loss, extinction ratio, figure of merit, and then we have compared their results along with our results, and then we have come up with the comparison table.
Okay. Yeah.
And here in table 5.1, it shows the structural parameter of different contemporary ITO-based optical modulators. So basically, it shows the thickness of the plasmonic material that were taken in the devices, which we have shown earlier, and the heights of the waveguide and the width of the waveguide. Then after that, we have compared the dimensions of the device shown in figure 5.5 along with our proposed devices, that is a V-shaped EAM with 220 nanometer height and 350 nanometer height. So this is a comparison table of thickness of ITO, then the waveguide height and waveguide width. So our device has a thickness of the plasmonic material of 12 nanometer for both the V-shape EAMs with 220 nanometer height and 350 nanometer height. However, the width of the waveguide for 220 nanometer EAM is 400 nanometer, and the width of the waveguide for the 350 nanometer EAM is 320 nanometer.
Yeah. Good.
To study the performance of the device, the FEM base or FEM method is used. A 3D FEM optical mode solver and frequency domain analysis in console multiphysics is used.
Uh, Himanshu,
Yes, sir.
are you reading that to study the performance from
Yes,
here?
sir. Yes, sir. Yeah. To study the performance of the device, the FEM method is used. A 3D FEM optical mode solver and frequency domain analysis in console multiphysics is used to calculate the ILER and the NEFF of the device. The refractive indices used in the simulation were 3.47, 1.98, and 1.44 for SI, HFO2, and SiO2 respectively. A meshing element size of 10 nanometer is used to accurately model the structure around the ITO-HFO2 layer interface. The input power is launched to the device by exciting the modes in the waveguide. The frequency domain analysis along with the power monitors is used to measure the power reaching the waveguide's end. Also, the device has been optimized by exploring the structural parameters like the waveguide width, waveguide height, and thickness of the plasmonic material used, respectively, along with its effect on the IL of the device at both on-state and off-state to find the suitable dimensions for the device. The waveguide's dimensions are well suited to work in a regime considered to be single mode with low propagation losses at the communication wavelength of 1550 nanometer. So here, figure 5.6a shows the IL over the entire C-band wavelength range, ranging from 1500 nanometer to 1580 nanometer for the V-shaped EAM with 220 nanometer waveguide height. So figure 5.6a, it shows the insertion loss for both the on-state and off-state over the entire wavelength range, that is the C-band wavelength range from around 1500 nanometer to 1580 nanometer for the electro absorption modulator, which is having 220 nanometer waveguide height. So here we can see that at 1550 nanometer wavelength, which is the low loss optical wavelength, here the maximum insertion loss at off state is around 7 dB per micrometer, and for the on state it is around 0.031 dB per micrometer. So therefore, if we calculate the off state and on state, from here we can calculate the extinction ratio. So the extinction ratio and figure of merit as a function of the wavelength ranging from 500 nanometer to 1580 nanometer for the EAM with 220 nanometer waveguide height is shown in figure 5.6b. So here there are two lines. One is corresponding to extinction ratio and one is corresponding to FOM, and both of them are having separate y-axes. So the black color line is for the extinction ratio and the red color line is for the figure of merit. So for the 220 nanometer waveguide height base EAM, the extinction ratio at 1550 nanometer was observed to be 7.02 dB per micrometer, and the figure of merit was observed to be around 226 for 1550 nanometer application wavelength. Similarly, if we come to figure 5.6c, it shows the insertion loss over the entire C-band wavelength for the 350 nanometer waveguide height EAM. So here at 1550 nanometer, we have observed maximum IL at offset of around 11.06 dB per micrometer, which is shown by the black line, and the insertion loss at on state at 1550 nanometer was observed to be around 0.025 dB per micrometer. And from here we can calculate the corresponding extinction ratio and FOM, that is a figure of merit, which is shown in figure 5.6d. Here the red line indicates the figure of merit and the black line indicates the extinction ratio. So the extinction ratio of around 11.04 dB per micrometer was observed at 1550 nanometer application wavelength for the device having 350 nanometer waveguide height, and a figure of merit of around 441 was observed at 1550 nanometer application wavelength for the 350 nanometer waveguide height based EAM.
Okay.
The insertion loss IL over the entire C-band wavelength range for the V-shaped ITO plasmonic base EAM with 220 nanometer waveguide height is shown in figure 5.6a. At 1550 nanometer communication wavelength, the IL at off-state and on-state was 7.051 dB per micrometer and 0.031 dB per micrometer respectively for the EAM with 220 nanometer waveguide height. The ER and FOM of the 40V shaped ITO plasmonic base EAM with 220 nanometer waveguide height were 7.02 dB per micrometer and 226 as shown in figure 5.6b. Similarly, the IL at offset and on state for the V-shaped ITO plasmonic base EAM with 350 nanometer waveguide height over the entire C-band wavelength range is shown in figure 5.6c. At 1550 nanometer wavelength, the IL at off-state and on-state were 11.067 dB per micrometer and 0.025 dB per micrometer respectively. The ER and FOM for the device over the wavelength ranging from 1500 nanometer to 1580 nanometer is shown in figure 5D. The ER and FOM calculated for the V-shaped ITO plasmonic base EAM with 350 nanometer waveguide height were 11.02 dB per micrometer and 441. The calculated ER and FOM for the investigated V-shaped ITO plasmonic based EAMs are better than most of the devices as shown in table 5.2. The capacitance C is equal to 22.7 femtofarad and 21.5 femtofarad for the V-shaped ITO plasmonic based EAMs with 220 nanometer and 350 nanometer waveguide height respectively, that can be calculated by C is equals to epsilon naught A by D, the parallel plate capacitor model formed at SI plasmonic dielectric SI stick. Epsilon naught is the dielectric constant of the dielectric material. A is the area of active layer. Epsilon naught is the free space permittivity, and D is the thickness of the dielectric spacer. However, the experimental capacitance may vary due to additional parasitics from disorder in film deposition, wiring, and making metal contacts. R is a system resistance assumed to be 500 ohm, reference 11. The device's modulation speed was 14 GHz and 14.8 GHz for the V-shape ITO plasmonic based EAMs with 220 nanometer and 350 nanometer waveguide height respectively, which is suitable for high-speed optical communication. Also, the E bit for the device was observed to be 112 femtojoule per bit and 106 femtojoule per bit for the V-shape ITO plasmonic based EAMs with 220 nanometer and 350 nanometer waveguide height respectively. Furthermore, the performance of both the devices can be enhanced in terms of ER and FOM by making structural design changes, and also by realizing different plasmonic materials within the device with a trade-off of higher IL, complex and large device footprint. Now here in table 5.2, it shows the investigated V-shaped ITO plasmonic based EMs compared to recently reported contemporary modulators. So different kinds of modulators are here. We can see that is reference 8, reference 9, reference 10, 11, 59, 60, and their parameters in terms of thickness of the accumulation layer, which is denoted by TACC, and extension ratio denoted by ER, insertion loss denoted by IL, figure of merit denoted by FOM, and energy consumption per bit denoted by E bit. So we are comparing these values with the values of the device which we have proposed, that is the V-shaped EAM, which is having a 220 nanometer height, and the V-shaped EAM, which is having a 350 nanometer height. So from this table, we can see that the V-shaped EM, which we have designed with 350 nanometer height, shows maximum extinction ratio, which is around 11.04 dB per micrometer. And comparing with other devices, this is the best value we have got. However, if we see the insertion loss of reference 8 is better than ours. Ours insertion loss was 0.025 dB per micrometer. However, the insertion loss of reference 8 is very less, which is around 0.003 dB per micrometer. Similarly, the FOM of our device is better as compared to most of the devices, which is around 441 and 226 for the 350 nanometer height EM and 220 nanometer height EM. Also, the energy consumption we can see is better than most of the devices. Not the best we can say, but it's better than most of the devices, which is around 106 femtojoule per bit for 350 nanometer waveguide height base EM and 112 femtojoule per bit for the 220 nanometer height EM. Now coming to section 5.4 summary, a brief summary of this chapter is as follows. Section 5.1 gives a brief introduction to the chapter. The structural design of V-shaped ITO-based plasmonic EM is elaborated in section 5.2. Section 5.3 discusses the aspect of the effect of change in structural parameters like the waveguide width, waveguide height, and thickness of the plasmonic material used. Also, the structure of contemporary ITO-based modulators is compared with the V-shaped ITO-based EM in this section, along with the performance matrices of the device.
Great. So ultimately, we have covered entire thesis, at least contributory chapters. Now only 3 more pages are there. Should we complete that one? Then we will discuss, or we want to discuss here?
So let us first complete this conclusion and future work.
Okay, that shall be good, because this will recall everything, and conclusion also. Okay.
Okay, so coming to chapter 6, that is conclusions and future work. So starting from section 6.1 conclusions, in this thesis, silicon optical modulators based on plasmonic materials have been presented with different structural designs and different plasmonic materials. Also, the optical characteristic of plasmonic materials have been investigated. Different structural designs like directional coupler based silicon optical modulator, a modified sidewall angle EAM, VO2 ITO based EAMs, and a V shaped EAM with different structural parameters in terms of waveguide height has been presented in this thesis. A rigorous FEM method is used to carry out the presented results. The device performance has been evaluated in terms of IL, ER, FOM, and EBIT respectively. In chapter 2, an introduction to the electro-optic modulators, different type of electro-optic effects and different types of losses in optical waveguide were discussed, which were important to measure, calculate the performance matrices of an optical modulator. Also, the CMT was discussed to know the mechanism behind the transfer of energy in directional coupler. In chapter 3, the architectural design of a directional coupler based optical modulator was presented with plasmonic material ITO sandwiched between two SI waveguides. The modulation in the device is achieved by the transfer of energy between the waveguides on the application of applied potential. Similarly, the design of an EAM based on modified sidewall angled SI waveguide was presented, which achieves better performance matrices due to its unique waveguide structure and use of ITO as the plasmonic material. Also, better performance were achieved by optimizing the structural parameter of the device. In chapter 4, two different EMs have been presented using VO2 and ITO with the same structural parameters, and their performance matrices are compared in terms of IL, ER, FOM, and EBIT. The material characteristic of VO2 have been discussed. The IL observed was very low in ITO, inside the bracket 0.025 dB per micrometer base EM compared to VO2 0.651 dB per micrometer base EM in the on state. The VO2 base EM shows better performance in terms of ER 5.85 dB per micrometer than the ITO 3.07 dB per micrometer base EM. Also, both the devices shows better performance in terms of IL, ER, EBIT, and FM as compared to most of the devices. In chapter 5, a V-shaped ITO-based EM has been presented and discussed. The V-shaped modulator's structural parameters were optimized in terms of the waveguide width, waveguide height, and thickness of the plasmonic material used to achieve better performance matrices. The V-shaped ITO plasmonic-based EMs with 220 nanometer and 350 nanometer waveguide height shows better performance than contemporary ITO-based EMs in the literature. A high ER of 7.02 dB per micrometer and 11.04 dB per micrometer were achieved at low IL of 0.031 dB per micrometer and 0.025 dB per micrometer in the on-state for the EMs with 220 nanometer and 350 nanometer waveguide height respectively. Section 6.2 Limitation of the present work. The limitations of the present work are as follows. The present work discussed different performance matrices of the device like IL, ER, FOM, and EBIT. However, the losses related to scattering and radiation were not discussed. Point number 2. Miniature devices integrated with plasmonic material have led to a family of new novel nanoplasmonic devices. The plasmonic material-based EMs can be used in high-speed communication system. However, the present work doesn't discuss about the data rates. Point number 3. The present work discussed different modulator designs based on ITO and VO2 plasmonic materials. However, other plasmonic materials like graphene, gallium oxide are unexplored in the present work. Section 6.3 Future work. The future scope of this thesis are as follows. There is further scope to design EMs based on other plasmonic materials like graphene, gallium oxide. Also, their performance matrices can be calculated in terms of ER, FOM, and IL. Further exploring the device's structural parameters like waveguide width, waveguide height, and length of the waveguide, polarization, insensitive modulators based on plasmonic materials can be designed and implemented. Different structural designs like slot waveguide, cross-slot waveguide, and T-shaped plasmonic-based waveguides can be used to design and implement an EAM with plasmonic materials. The fabrication of the presented EAMs and incorporating the devices in PICs and optical communication. At last point, efforts can be made to design a communication system based on optical modulators made of plasmonic materials like ITU and VO2 for high-speed communications.
Wow, great. This is the bibliography. You just have a look. GT read. This is the book. Some of the websites. And how many are there total?
Yeah, rounds are 80.
80 references. Okay, very good. So congratulations for completing this huge task. Reading a thesis itself is, very important task, and I, on behalf of all other members, also would like to congratulate, as well as congratulations goes to members also, those who have participated. Without their help, I think we would have not enough motivated to read, within 5 days. Total 5 days we have taken. That not even days, these 5 sessions, basically 5 sessions we have taken on an average 1.5 hour every day, and we have completed. So that is a good achievements, big achievements as far as read thesis reading is concerned. I think that maximum beneficiary shall be Himanshu Ranjan himself, because he has read now twice, it seems, because before coming to reading session he has already read once, so that he can nicely present, and after that he read in front of us, so that we can listen. So yeah, session is open to ask the question, to take advice from Himanshu, or what is next to go, because now we have seen what are the limitation as well as what are the future scope, what is leaving for others, so that one can carry forward. In nutshell, we have seen that he had designed a modulator, plasmonic material base, that is very novel material, synthesized material having excellent E and Z condition. See, through this activity, we want to tell that PhD is not so difficult task also, and it is not so easy also, unless one is serious and trying to attempt scientific method. So this is what we want to try to tell. In nutshell, we whatever plasmonic material we have taken on a particular voltage, on the application of a particular voltage, its characteristics drastically change from dielectric to metallic. That is the main thing. But within that, how can we improve its performance by changing its architecture? Okay. So in nutshell, these two things you can carry forward. And rest thing are just comparison, methodology, improving the accuracy, like that. So once one is on track, after that one can explore. So that is why number of more publication you can do. Although he has presented a lot of conference paper also, and he got best paper award in Optronics 2016. So this is the things. So we would like to hear from participants also. Please congratulate Himanshu Ranjan for this completion of reading. Now I think he must be feeling more confidence on his own thesis. Yes, Himanshu, what is your reflection? First of all, you say something.
So it was good to have a reading session. So because me also I haven't looked into thesis since I left Nehu. So now I could recall the points what I have done, and it was like a brush up for me. So thank you all for being there, for sparing time to listen to my thesis. Hope you all liked it. And if you have any queries or any questions, and if you want any suggestions, you can ask me now. It's a good platform.
Yeah, great. See, Himanshu could read because he has, he has to read, he has to defend, he has to get updated. But those who are participating here, they are coming out of their eagerness to learn something, to hear something. That is very appreciating. So, I'm very happy for turning up. And this this thesis, it was keep lying with me also, and not finding the time to read as a evaluator. In fact, I should have read, but yes, initially I have, while reviewing his thesis, what chapter by chapter I read that one, but independently I did not read. But now, line by line, I have also gone through. So it's advantage I am also getting. And uh, please speak out, these participants, whatever you could get, so that we should also know, because we only two people are talking, it doesn't this looks nice. Yes, Indrani, what is your reflection?
Yes, I have a question for Himanshu. First of all, thank you for reading this out to us. I wanted to know if you faced any difficulties or shortcomings when you were conducting this thesis.
So you are asking regarding thesis writing or regarding the work which I have done?
Regarding the work, I mean, with the whole process, I mean, what sort of shortcomings or difficulties you faced while working on this, and including writing out the thesis?
So let me divide the question into two parts. First of all, I will tell you the difficulties in writing a thesis, and the second, the difficulties I face in doing work.
Okay.
So first of all, let me go through the difficulties I faced in thesis writing. So if you have gone through my thesis this 5 or 4 days,
Yeah.
so I have done my thesis in LaTeX.
Okay.
So I don't know if you know or don't know to use LaTeX, but LaTeX, using
Yes.
LaTeX is a very, yeah, LaTeX using LaTeX is a very hectic process.
Yes, the whole, I mean, the whole syntax is very confusing sometimes
Yeah,
with all the
yeah, because
converting and
you
everything.
have to do some programming and you have to insert
Yes,
the
yes,
codes. It's not like Word that you just type the words and it will come. So you have to
yes,
put
yes.
some programming and all. But the output product is good. But
Mm.
while doing it, it was a very hectic process. So it took me, I would say, more than around 2 months to write the thesis itself. Although I have completed 50% of my thesis in Word, again I have
Yeah,
converted from Word to this LaTeX form. While conversion only, it took
yeah.
around 40 days.
Uh,
Means I already had
so,
all the materials of thesis in Word, but while converting from Word to LaTeX, it took me 40 days.
do you have any suggestions as to how we can like improve when we are using the latex?
Just go for these courses. No, some online courses are there. In SOT itself, they are organizing small seminars on LaTeX. So just go for that.
Mm. All
First
right,
of
okay,
all,
I'll
go
do.
for conference paper and go for like small papers of 2-3 pages and write some
Yeah,
documents in LaTeX. Practice it.
okay.
After that, go for thesis. Directly, if you want to write your thesis in LaTeX, then you won't be able to do it because you will
Yeah,
find it very difficult and you won't know how to solve your problem because LaTeX is a programming language, you can say, and lots of codes are required. Unless until each and every code is okay, it won't run. It will show
yeah.
you lots of error, lots and lots of error.
Yeah, I mean, I already have 5 errors on that page that I'm working on,
Yeah,
and,
so
and I
therefore,
still don't know where the error is coming from.
yeah. So this was about thesis. Now coming to the difficulties I faced in work is that first of all, you have to go through a literature.
Mm.
Literature means you have to read a lot of papers starting from the
Yes.
basics.
Yeah,
See, while reading, when you are a research scholar or even an MTech scholar, when you are reading a paper at the first time, or you can say the first 2 to 3 times, you won't understand the paper itself
yeah.
because most of all the papers are written in technical terms. But the
Yes.
thing is, as sir told in nutshell that I have done this, the same thing I will write in such a way that it will be very complex for you. You won't understand what I have done, what I am doing, and what is in the paper. That's why go through a paper more than 10 times from my side. After
Okay.
10 times, you will be able to understand what I have done. not the entire paper, but you will be able to understand what the author have done or what he is trying to tell you. First of
Okay.
all, go through the abstract, then try to understand the abstract. After that, go through the paper.
All right.
So, and also finding good papers is one of the main tasks.
Mm.
See, for a particular topic, you will have a lot of papers by a lot of authors.
Mm.
But finding an author who have done a genuine work is very difficult. And finding a paper which is suitable for you, means some papers are there regarding optical modulators only. The papers which I have compared, most of the papers are well written, and then they are from well organized authors from well organized institution, you can say.
Okay.
So always go for high quality papers and good papers. It is not like that somebody have written some paper which is very easy for you, that's why you have taken that paper as your base paper or reference paper. So don't go like that. Always choose high quality paper from high quality say journals like IEEE and elsewhere.
All right.
Especially
So
this go for SCI index journals. Don't go for like Indian journals which are
yes,
not index.
and keep that in
You'll
mind.
find that, yeah, if you go for Indian papers, if you do the same thing which they have done, you
Yeah.
might find your results different from theirs. Then you will think that you might have done something wrong, but actually the paper has something or some mistakes in the paper is there. That's why.
Um, okay, so when I'm sifting through the potential papers that I can reference or cite, so what should
Yeah.
I focus on? Should I focus on the number of citations that the certain paper has, or should I focus on the author or the institution?
See, the points we have, which you have told, all are good points only. So you should see all the points. First of all, good citation. If the paper has, then it's good. But the thing is, if it's a new paper, it won't have citation.
Yes,
If
yes.
the paper is published today, then it won't have any citations. But
Yeah.
it doesn't mean the paper is not good. The paper is good, but since it is new, it won't have any citations.
Yeah.
That's why go for good journals like IEEE journals are there. If you are in optic field, and journal of quantum electronics is there, then electronic later is there, and then if you see in elsewhere, optic is there, optic communication is there, laser and optics is there. Those are good journals, and also they are having good impact factors of around 2.4. All are above 2 only.
Yeah.
And then after that go for this authors. Always you see the institution from where the authors are. That is what I am following. Suppose the author is name is so and so, I don't know the author, but when I see his affiliations, okay, he have done from Stanford University, he is doing from like good universities like MIT, then Cali University of California. Those affiliations are good. So I always go for such kind of affiliations, because
Yeah.
author by name I don't know who he is. That's why.
Okay. Okay, so I just have one final question. When you said that you redrew the reference diagrams that you
Yeah,
cited from certain papers,
yeah.
how did you redraw it? I mean, I came across a few diagrams. I actually came across one signal graph, but I don't think I can redraw it in my own way since it's just a bunch of patterns and I don't
Okay,
have the required application for it. But on
okay,
the flip side, I have some certain flow charts with in block forms, but I can
okay.
redraw it. So how can I do that?
Okay, first of all, let me tell you, in my thesis there are 6 chapters. So out of the
Yeah.
six chapters, only chapter 1 and chapter 2, that is the introduction chapter and this electro-optic modulators chapter, those chapters I have redrawn.
Yes,
Others,
you told me that
yeah,
in the
the
previous session.
pictures and the graph shown in chapter 3, chapter
It was done
4,
by
and
your
chapter 5,
team.
those I have made personally.
Yeah.
Those for that I have used like one software is there, Origin. Have you heard?
No, I haven't heard of that.
Yeah, one software is there, Origin. You can go for it. That Origin is a very good software. Almost every scientific research person use Origin software for
All right.
graphs and for figures and all. For graphs, you can go for Excel also. Excel is also good, but
Yeah.
Origin it's like one of the best software.
All right.
So you can go for Origin, and you can And for like simple drawing, like I've shown you the device structure. For that I have
Yes.
used Google online drawing tools and Microsoft PowerPoints. These two I have used. And for
Okay.
graphs and all, I have used Origin.
All right. Okay. All right. Okay. Thank you very much.
Okay, thank you.
Okay, before going to next question, I wish to take one snapshot. Otherwise, people are leaving. So, so can you on your camera so that a nice picture can I can take, and then we can carry on our question answer. I would request everyone, please. Yeah, very good, Amartya. Malvinder, Rahul, Likinti, Deep, Sanjana, Hriday. Hurry up so that you can off your camera again.
Sir, it's too
Hello.
late, sir. It's dark.
Where is dark?
Sir, it's too late. It's dark.
Light is not there. Still you on camera.
Sir, it's dark.
Okay, that's okay. So let me take. Oh, किसी का आंख बंद रह गया. Sorry. क्या हो गया हिमांशु? हिमांशु,
Yes, sir.
yours one was closed. Now good. Thank you so much. It is better because getting good pictures simultaneously, it is really. इसका मतलब है sometimes it's good. There's no as a network issue. Anyway, so should I close this recording and then we have a chat? Yeah, stop recording.